Okay, so we'll be switching gears and talking about geochemistry, and so this is going to be a lot of just basics. And as I said here, I'm going to talk about what we think we know about the composition of the Earth, how we think we know that, and its gross evolution into core, mantle, and crust, and perhaps into distinguishable mantle reservoirs. So this is the outline. We'll begin by talking about meteorites and chondrites and chondritic abundances. One of the important concepts is volatile versus refractory elements. We'll talk about models of Earth's composition and the implications those have for, among other things, heat flow, or heat production rather, which in turn is the energy to drive terrestrial dynamics. Differentiation of planets into mantles and cores, and the concept here is that of lithophile versus siderophile elements. Then differentiation of the silicate part of the Earth into crust and mantle. We'll define what we mean by partition coefficients, and the key concept here is compatible versus incompatible elements. I'm going to talk specifically about, because they're very useful tools, rare earth elements and rare earth patterns, rare earth diagrams. We'll extend those into another favorite geochemist tool, spider diagrams. Talk very briefly about the concept of mobile versus immobile elements, because hydrous fluid transport also seems to play a role in differentiation of the Earth. And we'll show that the crust of the Earth is probably formed predominantly, perhaps not exclusively, by island arc volcanism. And we'll talk about the origin of mantle heterogeneity, chemical heterogeneity in the mantle that we can distinguish based particularly on trace elements and isotopes. Okay, so meteorites to begin with. Meteorites, the important thing about meteorites is the story of the early solar system formation of the planets. Two broad classes of meteorites. One are differentiated meteorites. These are parts of planetesimals, asteroids, that have differentiated into mantles and cores. The mantle parts being the achondrites. This is a eucrite, a piece of Vesta. The core part being an iron meteorite, which you can see there. But our main focus is on chondrites, okay, of which there's a variety of classes. Carbonaceous, ordinary, enstatite. You'll hear those terms not only in my lecture, but in some of the other lectures over the next couple of weeks. Okay, and so focusing on chondrites, what they're made of, primarily we can distinguish four principal components. So-called CAIs, which stands for calcium aluminum inclusions. These are condensates or evaporative residues that formed at very high temperature within the solar nebula. Chondrites are collections of nebular dust. That's why they're important. They're sampling the building blocks of planets, which was this nebula from which the sun and the planets formed. Second component, chondrules, which I guess this is a pointer. Okay, so here's an example of a chondrule. This is probably a CAI, but here's a chondrule. You can see it's spherical. These are once molten droplets, again, that formed within the nebula. Most often they're olivine rich, but other minerals and iron metal are common. They show evidence of rapid cooling and can account for up to 75% of the volume of chondrites. So a lot of nebular material was reprocessed as chondrules, hence the name chondrites. And meboidal olivine aggregates, which are microscopic, we can't really see here. These are also fine-grained, high-temperature condensates. And in the matrix, the black material here, tends to be richer in volatile elements. In some cases, such as this meteorite, Allende, The C designation here indicates carbonaceous chondrite. We won't worry about the V. I'll explain the 3 in a minute. The matrix of some meteorites includes so-called pre-solar grains. These are ejecta of supernovae and red giants, material that was incorporated in the meteorites without significant subsequent processing in the solar nebula. It was just this stellar debris within the solar nebula. How do we know? Because they have extraordinarily odd isotopic compositions. Okay, and these, just a little bit more on them. The most common, actually, I'm not sure they're the most common, but the earliest found ones are silicon carbide, graphite, and very, very fine diamond. And these silicon, graphite, these are among cosmically the most abundant elements, the kinds of things that would be thrown off by stars. But it's mainly their extraordinarily strange isotopic compositions that tell us that they're pre-solar. In some cases, these isotopic compositions can be related to specific nucleosynthetic processes, such as slow neutron capture in red giants, or rapid neutron capture in supernovae. Very good question. Okay, anyway.
When you're talking rapid cooling, what sort of timescales are we?
Hours or less.
But never quick enough to see glass.
Yes, no, they do include glass. They are glassy and partially devitrified glass. Yes. Where they're preserved, they include glass. Yes. Okay, significance of chondrites. Okay, although all our meteorites were parts of planetesimals or asteroids. They're bits of asteroids. Okay, and so they've invariably been modified or altered to some degree on their parent bodies. And there's this scale, this number refers to the extent which they've been altered. Petrologic grade 1 and 2 is hydrous alteration, as in this Murchison meteorite. 3 is the least altered; those are the most pristine. And then 4 to 6 indicates increasing thermal metamorphism. But again, they are composed of nebular dust, the raw materials from which planets are built. The compositions do vary. This is why we have a variety of classes of chondrites. By the way, probably each class represents a single parent body. They vary primarily in the ratio of volatile to refractory material, in oxidation state, and in the ratio of metal to silicate. One particular class of chondrites, the CI group, which, by the way, contains no chondrules, but it's classified as a chondrite because it is primitive material, nebular material. Best matches solar composition. So this is what Bill was talking about earlier. This is the log abundance in the solar photosphere determined spectroscopically. And this is the log abundance in CI chondrites determined by other analytical methods. You might ask, well, if we know the composition of the solar photosphere, why do we bother with chondrites? Because we can't measure trace elements that accurately in the solar photosphere, and most elements are trace elements. So this really tells us the composition of the solar nebula. Why is that the same as solar? Because the mass of the sun is some 99% of the mass of the solar system. So the mass of the composition of the solar system, the composition of the solar nebula from which all these bodies formed, is the same as the composition of the sun. Okay, now, where we find elements, the various elements in chondrites, depends largely on their volatility. And we'll get into this in just a minute, but the most volatile elements typically are found in the matrix. Here's another CV3. The main group elements, which I'll define in a minute, these are the most abundant elements, silicon, magnesium, iron, things like this. are predominantly found or make up at least the bulk of chondrules. You can see in the case of this meteorite how large a fraction of it is actually composed of these chondrules. And then the most refractory elements are concentrated in these CAIs. I'm going to talk here about, in a minute, next slide should show you a slide of condensation temperatures. And I just want to make it clear that these condensation temperatures are not the boiling points. If you click on a periodic table or something, it's likely to tell you the boiling point of an element. This is not really relevant because things condensed as compounds, not as elements, from the solar nebula. So aluminum, for example, has a rather low boiling point. It's actually, as a metal, it's rather volatile. But it condenses as an oxide. It's highly refractory. Carbon, on the other hand, the sublimation point of graphite is extremely high. But it condenses at very low temperature because mostly it's oxidized to CO or CO2. Okay, so this is how and before I get to that, this is why it's important. There was likely a very strong thermal gradient within the solar system, such that here's Earth, Venus, Mars, the asteroids, such that at least at one point, perhaps almost everything, perhaps the exception of these CAIs, was in fact in the gas phase. The nebulas is a mixture of gas and dust. As it cools, the fraction of dust grows, but the nebula is composed almost entirely of hydrogen anyway, so most of it's gas. So there's this very strong thermal gradient, and to some degree, this is also reflected in the compositions of these planets. So the giant planets and the outer icy planets are composed of water ices, ammonia, hydrogen, helium, methane, etc. The inner planets composed of silicates and iron. So the reason is that these inner planets probably formed while the solar system was still hot. So there was no opportunity for the more volatile elements to condense and accrete to these inner planets. Okay, so now let's define what we mean by, in a sort of quantitative sense, what we mean by refractory and volatile. So this is the 50% condensation temperature in kelvins of calculated condensation temperatures of elements in a low-pressure nebula, something like 10 to the minus 4 atmospheres of solar composition. And the first thing to condense, actually rhenium, osmium, metal, things like tungsten, zirconium, hafnium, oxides of those. Where's calcium? Calcium should be in, oh, there it is. Calcium and the rare earth elements, also uranium, thorium, two important elements that come up in discussion are neodymium and samarium. It condense almost at the same temperature. Titanium, another very high temperature element. Platinum, the platinum group elements are also all refractory. So everything that condenses above this group of elements, the main group, nickel, iron, silicon, magnesium, chromium, we consider refractory. Everything that condenses at temperatures below that, we consider volatile. And Bill mentioned potassium, for example. That's a relatively volatile element. Yes?
Bill, Michael Magna from Berkeley. Why is there a 50% condensation temperature? Why is there not a simple?
Because I guess because it's a complex reaction sequence. We're actually condensing minerals and complex phases. And I guess the convention is just to choose 50% as a reference. So you would, for example, you might condense a bit of uranium up with say zircon in perhaps some phases, but right. So even these higher temperature condensates may contain a small amount of this lower material, right. And some of these things might not completely condense until lower temperature. So yeah. So I guess that's the point. Everything actually condenses over a range of temperatures, not instantly. And so that's just a reference point. Is there another question?
you comment on the uncertainties in the half-mass condensation temperature?
The uncertainties in the condensation temperatures. No, I can't. Katrina Loder's in her 2003 paper, I think, has that information on. No, not really. But I guess the thing I'd say is people have been working on this for decades. It hasn't really changed substantially. The early work by Goldschmidt and Larimer, I don't think is substantially different than this.
No, but some people have been asking why certain elements have been changing by 10 or 50 degrees Kelvin. I don't personally have that insight. I would go back to say that the origin of this scale really relates to condensations at the back end of nozzles of rockets. That's actually where the Johnif tables had their starting point. And I suspect that 50%, half the mass, is a engineering phenomena. So, yeah, they're all calculated temperatures for the calculated molecules. I would love to see a better assessment of that, particularly for the moderately volatiles, the ones that are in purple color there. They actually have changed around. And when Katerina's 2003, you'll notice where sodium is and potassium, and see where rubidium is. It used to be the other way around. It used to follow the periodic table: sodium, then potassium, then rubidium.
Yeah, that's true. There have been some changes. That's right.
It's become a head scratcher to me.
Right. Right. Yes, certainly there's some uncertainty, but you're never going to put potassium over here or aluminum over here. So I think this probably works for our purposes here of dividing elements into refractory and volatile. Okay, and this is going to become important. This idea of refractory elements will become important in defining composition of the Earth, and also in some of the things Rich Walker is going to be talking about later on in the week. Okay, the other way in which chondrites vary in their composition. So, right, I guess I should go back here. So, and say that chondrites vary. For example, some chondrites are much richer in refractory elements and much poorer in volatile elements than others. In general, for example, the carbonaceous chondrites are relatively rich in the volatile elements compared to refractory elements. So that's one of the ways in which chondrites vary. Suggesting this is one of the ways in which the dust in the nebula varied. A couple of other ways in which the composition of the dust varied, and that is the oxidation state. Among chondrites, we can go from things like Enstatite chondrites, which are in which the iron is basically completely reduced to metal, to carbonaceous chondrites, in which the iron is completely oxidized. And this is actually it's called a Urey diagram. It was Harold Urey who first began classifying meteorites this way. This is the ratio of iron metal to iron to silicon. This is the ratio of oxidized iron to silicon. These are lines of constant iron-silicon ratio. So you can see, and these are different classes of meteorites. And you can see they vary both in the total amount of iron to silicon and in the extent of oxidation. So carbonaceous chondrites, plotting down here, completely oxidized. Enstatite chondrites, completely here. And by the way, there are two groups, these so-called EL, the low iron Enstatite chondrites, and the high iron chondrites. And the rest of these are the so-called ordinary chondrites. Okay, so standard theory says terrestrial planets form by a process of accretion and oligarchic growth. I won't get into this in detail, but the idea is you build things by colliding little things and having it stick and get bigger and bigger until you get terrestrial planets. Just say briefly that this starts off at very fast. You go from dust grains to to small asteroids very quickly. And then the thinking is the process slows as you have less and less frequency of collisions. As you concentrate matter in bigger and bigger things, the process tends to slow. In any case, we now know that things the size of Vesta would have formed within a few million years from evidence from extinct radionuclides, gives us a time scale of these events. So within a few million years, things the size of Vesta with 3 to 500 kilometer diameter, I forget exactly. So that size of thing grows very quickly. And simultaneously with growth, essentially, it differentiates into a mantle and a core, and most likely a protocrust, a melt residue from the impact-induced melting. In the case of Vesta, which likely seems to have formed quite early, aluminum-26, a short-lived radionuclide, would have been a significant energy source to help melt it.
How small does a chondrite, a pre-chondrite body have to be to keep it as a chondrite?
How
big do chondrite bodies come from? Sort of
in terms of it's hard to say from the chondrites themselves. We have a better constraint from iron meteorites because they would have been hot. The cores of these things were initially liquid, and from diffusive profiles, you can sort of calculate cooling rates and therefore body size. I think it ranges up from 10 kilometers to 100 kilometers or so in excess. So even at tens of kilometers, we're already differentiating planets. Yeah, but the chondrites mostly, for the most part, the chondrites. Well, actually, I don't know about the metamorphosed chondrites. It's harder to say, but the carbonaceous chondrites mostly they're not highly metamorphosed, and they would have never been deep in a planet. So they would have never. The carbonaceous chondrites never experienced significant heating.
I was at a meeting recently where they discussed that maybe Vesta wasn't fully differentiated, and the idea was that the aluminum-26 actually goes into the crust, right, when it starts to form a crust, and therefore you don't get a lot of the heating on the interior of the planet or the body. So I wonder if there is this size, I guess this is more a dynamics question, but is there a size with which you will definitely have a differentiated body? And is there some
Well, I think the answer I just gave to Bruce in the sense that the cooling rates of, and you can correct me if I'm wrong, Rich, but I think the cooling rates in the iron meteorites, even at the size of tens of kilometers bodies, you have differentiated into mantle and core. And the idea that aluminum-26 contributed to this is fairly recent, based on this extinct radionuclide dating. We used to think that things like Vesta took a long time to form, but now the evidence is they're probably formed and differentiated quite early.
Two things. First, some people have recently been arguing that some iron meteorite plant bodies are actually pretty big, 500 kilometers across or larger. So we may be talking about pretty large bodies. And number two, tungsten.
At the upper limit, but the lower limit is still pretty small.
Yeah, and number two, the age of most iron meteorites is probably older than chondrite formation age.
That's the other thing that from palladium silver dating, we also know this idea of core formation happens very, very soon. Right, a lot of things, the conventional thinking in the past was chondrites were the oldest things, all these differentiated bodies were younger. Some of this short-lived radionuclide dating is almost turned that on its head. So we know some of these the point is this differentiation starts to happen in relatively small bodies, happens very soon. Okay, so, and what this means is what I said to Bill, when we're talking about accretion of the Earth, we're probably talking about bodies we're accreting bodies that themselves have already undergone some differentiation. Okay, now, how bodies differentiate, well, let's see. Where elements go in planets depends on, by and large, whether they're lithophile, rock-loving, or siderophile, iron-loving. Chalcophile refers to sulfur-loving, atmophile means things that tend not to condense. Mostly we're going to be concerned with siderophile versus lithophile. Siderophile elements go in the core. Most chalcophile elements are also at least somewhat siderophile. And regardless of how much sulfur there is in the core, the chalcophile elements are concentrated probably to a significant degree in any case in the core, versus the lithophile elements which constitute the silicate parts of bodies. Now, just a caveat, the exact partitioning, we'll introduce this later, of elements between cores and planets depends on temperature, pressure, and composition. So things that, so sometimes it can be difficult to draw a line, say this element is siderophile, this element's lithophile. Some elements we normally consider lithophile. Silicon, for example, niobium for another. Under certain circumstances, conditions of temperature, pressure, and composition could behave somewhat siderophile. Okay, and so eventually planets and planetesimals differentiate into atmospheres, at least for the larger ones that can retain it, with the atmophile elements, siderophile elements in the core, lithophile elements in the mantle and crust. And the mantle also then, at least in the case of the Earth, undergoes subsequent differentiation into forming a crust. And here are the differences between incompatible elements, those that aren't accepted in minerals and therefore concentrated in the crust when the mantle melts, and compatible elements, those that remain in the mantle. And we'll talk about that in a little more detail in a bit. I'm not going to talk I don't have time to go into composition of the core, just the idea that it formed very early. Rich will be getting into those complications in his talk. Okay, so now we're talking about differentiation or the trying to estimate the silicate, the composition of the silicate part of the Earth. And generally we start from these assumptions. First, the idea that the Earth did indeed form from a solar nebula of chondritic composition. But again, chondrites vary in composition. The nebula apparently wasn't homogeneous. So this gives us a little flexibility, but nevertheless, the Earth formed from this solar nebula, and any successful model of the Earth's composition must somehow relate to chondrites through some plausible processes. The composition must match seismic and density profiles of the Earth. The composition of the mantle, at least the upper mantle, should match that of the mantle sample, which are the peridotite xenoliths. Also, upon melting, the composition of the upper mantle should yield basalt. And we'll define this term bulk silicate earth, a bulk silicate earth composition. That means the composition of the crust and the mantle. And this is synonymous with the term primitive mantle. The reason being is the thinking is that while the core forms immediately, simultaneously with formation of the Earth, formation of the crust is a process that occurs over geologic time. So stuffing the crust back in the mantle gives us so-called primitive mantle, the mantle before the crust was extracted. Okay, so another important point is that despite the relative variety of chondrite compositions, the relative, although not the absolute, but the relative abundances of the refractory lithophile elements are very similar in all classes of chondrites. This implies that nebular processes were unable to fractionate. And by fractionate, I mean change the ratio of two elements. Were unable to fractionate refractory elements from one another. Okay? So this is a very important assumption. And most models of Earth's composition rely to varying degrees on the assumption the Earth also has chondritic relative abundances of refractory elements. And these are, so we've looked at the periodic tables, divided things into siderophile and lithophile. We're now dividing things into refractory, which are in red, refractory lithophile, which are in red. Notice that includes the rare earths, both the lanthanide and the actinide rare earths. Two very important elements because they're the principal sources of energy creation in the Earth. The green elements in green are these main group elements. And the other group that's important are the refractory siderophile elements, which are these, and which Rich will be talking about in his talk. What's it?
Why is cobalt included as
Why is cobalt? Because it condenses at main group temperatures. Oh, and cobalt is one of those elements that actually partitions between mantle and core, so that there's some cobalt in the core and some in the mantle. And it's one of the things that the people who figure out the conditions under which the core formed want to try to match. They need to get the right composition, right amount of cobalt left in the silicate earth and so that's again a TPX, temperature pressure composition matter of getting cobalt right. Okay, so what we call the geochemical class of models of the composition of the Earth begin by estimating the concentration of the major elements, the most abundant elements, from concentrations in peridotites. So this is a diagram from Palmy and O'Neill in 2003, in which they had already argued that the mantle had about 36.7 some odd percent of MgO, and these are compositions of peridotite xenoliths and also, I think, exposed peridotite terrains, and they simply regress the concentrations of these elements against magnesium. Basically, this is what this is partial melting. Things rich in magnesium have lost melt to form the crust. They're depleted in calcium, aluminum, and silicon, consequently. So they just take the intersection of these correlations with their assumed magnesium composition. They also have already, at this point, determined an iron composition, an iron concentration for the mantle. And then once you know calcium and aluminum, because these are refractory lithophile elements, you can assume that the ratio of other refractory lithophile elements, so some of the things we're going to be interested in: uranium, thorium, strontium, niobium, tantalum, and importantly the rare earths, which I'll be talking about. Those are all refractory lithophile elements, and we assume that the ratio of those elements to, say, calcium in the Earth is the same as it is in chondrites.
What do you think how critical is it, or might it be important that these geochemical models based on peridotite xenoliths are xenoliths mostly derived from the continents with deep, old, cold continental lithospheric roots, and that we don't have xenoliths from the convecting mantle to our models? Because a lot of people in this room, our community, is concerned with the dynamics of the convecting mantle, yet many of our geochemical models are based on a very particular sample.
My answer is, yeah, I'm slightly worried about that. But on the other hand, we do have limited suites of xenoliths from oceanic areas like Hawaii and a few other places. And they don't diverge significantly from these correlations. So, but that is a little bit of concern. It always worries me that our primary peridotite sample is in fact the continental lithosphere, for which we don't. He's not worried about it at all. Is what he's trying to say.
Well, I'd say that there is a subgroup of samples that are from xenoliths. And I'm familiar with some of the people who've been involved in this work, and yes, they do use massif peridotites, and they also use ophiolite peridotites to look at it. Massif peridotites are, of course, they're on the sides of continents. They're at the edge, but they have an appearance that look like they could be from the convective mantle in terms of their chemical and isotopic characteristics, and so too ophiolite fragments. But you could always argue that these subdomains of the mantle may not be exactly equal to the asthenosphere.
I guess the thing I'd add is that it's more likely that the convecting mantle lithosphere and lithosphere diverge in the concentrations of trace elements, and these are not estimated this way. As I said, we get the refractory lithophile elements by this ratio to these major, to calcium and aluminum. So, yeah, yeah, Rich.
There are also places on the Earth where the Earth has conveniently removed the old lithospheric mantle and replaced it with new, like the North China Craton. So the peridotites you get from some parts of the North China Craton are really pretty young and presumably are sampling relatively recent mantle.
Okay.
And they don't diverge in these. No.
Yes, Barbara?
You mentioned that all of this depends on already determining the magnesium. How is that?
They argue, for example, that it's pretty well established that the so-called Mg number of olivine, the ratio of magnesium to magnesium plus iron in olivine in the most primitive peridotites is pretty close to about 0.9. And that allows them to deduce magnesium concentration and the iron concentration. So they start out with the composition of olivine in the most pristine peridotites to get that. Okay, so then we get the refractory lithophile elements. How do we get the rest of the elements? It turns out that there are element pairs whose ratio tends to be rather constant in a great variety of things. So this is again a slide from Palmy and O'Neill. There's mid-ocean ridge basalts, oceanic island basalts, island arc basalts, komatiites, peridotites, all plot along a line here. It's a log scale, so there's some significant scatter. But this is samarium concentration versus tin concentration. And that line, of course, gives you a ratio of 0.32. And you can see it's quite different than in the CI chondrites. And tin is a relatively volatile element. No particular reason why the Earth should be chondritic in its tin-samarium ratio. Rubidium-barium ratio, myself and Al Hoffman showed that to be rather constant, about 0.09. Barium, a refractory lithophile. Rubidium, a non-refractory, a volatile lithophile element. And of great interest is the ratio of potassium to uranium, because potassium is the third heat-producing element. And long time ago, Wasserberg and others pointed out the potassium-uranium ratio of the Earth seemed to be constant around ratio about 12,000. And pretty much subsequent work keeps coming in at numbers around that. So, for example, Rudnick and Gao, the now standard estimate of crustal composition, the ratio is 11,300. Most recent estimate of Moore, but Gale and others, a ratio of 13,000. My student Paul, we looked at OIB's ratio about 11,000, so somewhere around 12,000. So if we know uranium, we can calculate potassium. And using that kind of thing, we can build up periodic table. I need to go back. Yes? Okay, right. I am going to define those better, but no, there's no room to. In a minute, I'll show you the important difference. Morb is mid-ocean ridge basalt. It's the basalts that erupt along divergent plates boundaries. OIB, oceanic island basalts. These are basalts that erupt at oceanic islands like Hawaii. Let's see. I guess I'll get into that in more detail in a moment, but or later on in the talk. Let me just say that peridotite exposures and peridotite xenoliths are rare. So geochemists, whereas basalts are quite common. So in fact, geochemists depend heavily on the basalt sample for understanding the mantle. Basalts are partial melts of the mantle, and their composition is not identical to that of the mantle. But yet, I guess the point is here that the samarium and tin are not fractionated by the melting process. Okay, so although basalts don't equal mantle composition, elemental ratios, some elemental ratios in basalts are the same as in the mantle. And isotope ratios in basalts are the radiogenic isotope ratios are the same as in the mantle. So basalts are an important part of the sample. Okay, anyway, we end up with an estimate of bulk silicate earth composition like this. This is actually McDonough and Son turned into a log scale. Notice that there's only 6 elements that make up more than 99% of the bulk silicate earth. In that sense, everything else, most of the periodic table, is a trace element. Okay, there are some competing models. And this is, okay, so there's a lot of numbers here. The ones I want you to look at are the ones in red. And first of all, if the Earth were a CI chondrite, you can see, 22% silicon, 23% iron. If we took out a core, we'd end up with 50% silicon, 6% iron. All these, 45 to 46% silicon, 7 to 8% iron, about 37% magnesium. There really is pretty good agreement. These are the standard geochemical models, various versions of them. And there's several more. I don't have room to put them all up. But pretty much they agree pretty well. The Lubetskaya and Kornaga take a somewhat different approach. It depends more heavily on statistical treatment and less heavily on, let's say, cosmochemical assumptions. They're a little different, a little richer in magnesium. Importantly, a little poorer in potassium, because again, that's a heat-producing element, but still, pretty good agreement. But then there's a couple of other models that I want to talk about briefly that are quite different. Javois' Enstatite chondrite model is different for a lot of things. The O'Neill and Palme model is different almost only for potassium. Let's talk briefly about what these competing models are. First of all, Marc Javois has pointed out that, and as other people, that if we look at oxygen isotopic composition, and this is a measure of oxygen isotopic composition that cannot, a part of the composition that cannot be explained by normal chemical fractionation. And this is the isotopic composition of chromium. the epsilon, and we're talking about very small differences. The epsilon symbol indicates differences in parts in 10,000. The delta symbol indicates differences in parts in 1,000. So we're really talking about very small differences in isotopic composition. What he points out is that Enstatite chondrites by far best match the isotopic composition of the moon and the Earth. And only just within the past month or two, there's a paper come out to show that there, in fact, is a very, very small difference in oxygen isotopic composition between the moon and the Earth. But we really match that of Enstatite chondrites. We're nothing like, these are the carbonaceous chondrites. These are the ordinary chondrites. These urolites are achondrites. But anyway, so isotopically, Enstatite chondrites actually best match the composition of the Earth. And this is true of a few other elements as well, but not true of one really important element. The other thing is the Earth, in fact, is actually pretty reduced. We live on the oxidized surface, but on the whole, a very substantial fraction of the iron in the Earth is, in fact, metallic. It's actually a pretty reduced planet. So in that sense, we're more like Enstatite chondrites than perhaps ordinary or carbonaceous ones. On the other hand, the silicon isotopic composition of the Earth is very different from that of Enstatite chondrites. It's a lot less different from that of ordinary chondrites. Now, you can explain the difference between ordinary chondrites and the Earth if you put 6, 7, 8%, and that would know more about this, silicon in the core, because there's an isotopic fractionation that occurs when you reduce the silicon. And this is about the amount of light element you need to put in the core to get the density right. So that's perfectly acceptable. On the other hand, if the bulk Earth has a silicon isotopic composition of Enstatite chondrites, we would have to put something like 28% silicon in the core, which is outside the geophysical constraints on density. So the model fails in that sense. Also, his predicted mantle composition is really quite different from what we observe in peridotite Xenolith suite. This requires a layered mantle, or at least the parts of the deep mantle that are very different in composition from the upper mantle. Okay, the other model, what we'll call collisional erosion, pushed by O'Neill and Palme, but also other people, Caro and Bourdon and myself, Matt Jackson, are all fans of this. Have noted that the Earth actually has excess neodymium-142. I'm not going to go into this. Other people will, perhaps. And that's a product of the extinct radionuclide samarium-146, which has a 68 million year half-life. We should not have that excess if the samarium-neodymium ratio of the Earth were the same as chondrites. The samarium-neodymium ratio of the Earth should be the same as chondrites, because these two elements condense within about 50% condensation temperatures, or within 10 degrees of each other. Both refractory lithophile elements. Doesn't look like the nebula can fractionate them. Okay, so that led to the hypothesis that the planet building process perhaps was not conservative. Specifically, as planets grow, magma oceans form, and then they form this crust. The crust is enriched in incompatible elements. The idea is that then crust is then blasted away by, not all of it, I think you need to blast away something like 15% of it, something like that, blasted into space by collisions. And so we would lose a low samarium neodymium protocrust to space that would leave the Earth having a high samarium neodymium ratio, accounting for this excess 142. The important implication here is that the Earth would have lost a significant fraction of other incompatible elements, most importantly the heat producers, potassium, thorium, and uranium. The alternative explanation to this which is not really the alternative, it was the original explanation put forward by Boyer and Carlson, was that in fact the protocrust formed, but instead of being blasted away, it sunk into the deep mantle where it's stayed ever since. This is their so-called early enriched reservoir, the EER, and one possibility is these large low-velocity shear wave provinces are just this reservoir. To make the geochemistry work, you need to put something like 40% of the heat production within these things. The other point is because of the very short half-life of this samarium-146, which alpha decays to neodymium-142, you have to do this very early. You have to do it, and the other point is the Earth and the Moon share the same anomaly. You have to do it before you form the Moon. You have to do it well before you form the Moon to account for as much excess 142 as there seems to be. That's a problem we have in Earth's composition. Yes? Can somebody give him the microphone?
The Earth has been made up of these chondrites, correct?
There's what?
The chondrites are the building blocks for the Earth. So is there any reason that the Earth should have one particular makeup of a chondrite rather than another? Is there like a just simple explanation for that?
Okay, good question. As I said, the carbonaceous chondrites actually seem to be the best preserve the composition of the solar nebula. But isotopically, particularly in their oxygen isotopic composition, they can't be the building blocks of the Earth. So, there is isotopic variation in the solar nebula, which say rules those out as being the main building blocks. The isotopic compositions favor the Enstatite chondrite model in terms of and also the carbonaceous chondrites are much richer in volatile elements. I guess the point is that we can throw out is building the Earth exclusively out of some classes of chondrites. We can throw that possibility out. I think, but there's no reason why the Earth couldn't be built out of a variety of kinds of chondrites. That certainly works, and that's certainly being specifically proposed. The other point, and Bill loves to remind me of this, is it's highly likely that it's highly unlikely that our chondritic sample is truly representative of the variety of materials that are in the solar nebula. The exposure times, the cosmic ray exposure times of meteorites, the amount of time they've been floating out in space as small rocks, for the chondrites is typically millions or tens of millions of years. This means that we're only collecting what's been thrown into Earth's orbit over the last few tens of millions of years. And these are undoubtedly as a result of close calls or collisions in the asteroid belt that are throwing things our way. There's no reason to think we have a complete sample. So we may well build the Earth out of yet another unidentified class of chondrites.
Do we have like a statistical distribution of what chondrites are out there, where they are?
Yes. Spectroscopically, there's you can identify certain asteroids or associate certain asteroids with certain classes of meteorites, and it appears, for example, the carbonaceous chondrites are the ones furthest out in the asteroid belt. This should improve as we get more data, as we begin to, for example, Ceres, which Dawn's going to visit next year, has a reflectance spectrum of carbonaceous chondrite. What it really is, we'll find out when Dawn gets there. But
I guess like my train of thought, why I'm asking this is, if there's certain types of chondrites that are further out, they probably have a less chance of interacting with the Earth. So is there like a linear sum of the ones that statistically should make the Earth what it is now? that we could maybe predict
Um,
using some type of accretion model?
I'm not sure that there was a paper, I think, Fitoussi and Bourdon, who thought they could mix a certain amount of ordinary chondrite with something, and people have done this.
I mean, because ultimately they all form from the solar nebula, so there
Right.
should be some distribution of elements where they are, depending on how it cooled and certain where it cooled, and then ultimately everything came from the same place. So why couldn't you sum it all together? Like, huh? Well, I mean, if there's,
What's the correct composition?
I'm not sure what the question is, but
well,
you
I mean,
probably
we know the composition of the Earth now.
you probably form planets.
No, but I mean, like,
The point is we're using these to try to guess what the composition
guess the interior. But I mean, using what we know about the surface, like, could you not put some constraint?
I think I mean,
There's certain building blocks, right? And we know. Yeah.
and we don't necessarily have all of those.
Okay.
So dynamically, there is a higher probability of having preserved bodies that were further out in the solar system.
Yeah.
Dynamically, you might have lost or in a solar
Okay.
system material. Like it's a you can play it, but it's not necessarily useful.
Yeah. Okay, I better. Right. Well, yeah, we better move on here. Okay. Implications for heat production. These models typically give us about 20 terawatts. Lubitskaya and Korenaga a little bit lower. The eroded Earth models, collisional erosion models, anywhere from 12 to 16. And Jouvin's chondritic Earth, or Enstatite chondritic Earth, is as low as 10. This is the URI ratio. It's the ratio of heat production to heat loss. And at a maximum, the Earth is probably producing only producing heat by radioactive decay at a rate of only half of what it's losing it. In these conventional models, in the other models, it's lower. In the extreme case, it's only a quarter. Okay, so now I want to talk about differentiation of the silicate part of the Earth. An early protocrust likely formed as crystallization of magma oceans or ponds as a result of energy expended during accretion. It seems to have happened on Vesta and the Moon, but there's no vestige of that protocrust. We have nothing of that age that's preserved. And while the core formed early, as I said, the present crust has grown by melting of the mantle over geologic time. There's much debate about the rate which it's grown, also the rate at which it might be destroyed. Partitioning of elements between mantle and crust depends on an element's compatibility. So this is the next key concept. And to define that, we're going to define a partition coefficient, which is simply the ratio at equilibrium, at chemical equilibrium, the concentration of an element I in phase alpha to the concentration of element I in phase beta. When our two phases of interest are liquid and solid, the convention is to put the concentration in the liquid in the numerator, concentration in the solid in the denominator. So I'm going to talk about liquid-solid partitioning. Rich will be talking about metal silicate partitioning, and partition coefficients will be defined in an exactly analogous way. Okay, incompatible elements are those that have solid liquid partition coefficients much less than 1. Compatible elements are those solid liquid partition coefficients about 1 or greater. And these terms refer to partitioning between silicate melts and phases common to mantle rocks, that is peridotite. It's that phase assemblage that determines whether a trace element goes into the crust or stays in the mantle.
This is the opposite, right?
Yeah, I think you had it wrong in the slide.
Did I?
before.
What?
No, the slide before that had it
This is
backwards.
correct, but
This is correct, the last slide. Yeah, it should be solid over liquid below.
Oh, you're absolutely right.
Yeah. So all
you're-
of these and all of these.
You're absolutely right. Jeez. Stupid. I'm glad you did that. I'm glad you pointed that out. Yeah. Right. It's solid liquid because, yes, right. Great. Okay, and the partition, for most of the elements of interest, a lot of these lithophile trace elements, just two things dictate their behavior, and that is their ionic size and their ionic charge. This is because these things, these atoms or ions, basically behave as hard charged spheres. Their charge is spherically symmetric to a first approximation. And so the only things that matter are size and charge. For the transitions, particularly the first transition series elements, the behavior is more complex. Many of these are compatible elements, but this is a contour of contours of partition coefficients, and things that there's most similar in ionic charge and ionic radius to iron, magnesium, and calcium. These are going to be the main among the main elements in mantle minerals. Silicon's typically too small, the site to accept substitution. So these are the substitutable sites. And the more different an element is in, say, for example, its size, barium's really big, so it has a very small partition coefficient. On the other hand, tantalum and niobium are about the right size, but they're highly charged, +5. They can't substitute in to that site, which normally wants a +2 ion.
Bill, where did you get that plot? That's a nifty plot.
I made it.
I've never seen a plot like that. That's very cool.
Oh, well, I made that particular plot, but I made that because I saw somebody else had done it. So I must say, so I can't claim complete originality. I think it might be in one of Wood's papers or something. Anyway, okay, so very quickly, batch melting model. Talk about how elements partition when the mantle begins to melt. The batch melting model is the simplest and probably least realistic of these. We can start with a simple mass balance equation, which says that the concentration in the original solid is equal to the concentration of an element I in the solid after melting begins, times this. F is the fraction of melt, so 1 minus F is the fraction of solid. This is the concentration of liquid times the fraction of liquid. So it's just a simple mass balance equation. We can substitute in our partition coefficient and rearrange things and get an equation like this. The important thing is to imagine what happens if F is equals 0. For an incompatible element, the maximum enrichment is simply going to be the inverse of the partition coefficient. On the other hand, let's imagine that we have a highly incompatible element and D is approximately 0. In that case, the enrichment is inversely proportional to F, to the fraction of melting. So that's important to think about it. Now, I want to use that. And talk about the rare earth elements, which are these elements down here on the bottom. We've already talked about neodymium and samarium a little bit. Promethium does not have a long-lived stable isotope. The rare earths are all in the +3 valence state, except sometimes cerium and europium can be in a different one. We won't worry about that. Again, they behave as hard charged spheres. Valence electron configuration similar. Ionic radius simply decreases from lanthanum up here about 127, if I recall correctly, something like that, picometers, down to lutetium, the heaviest rare earth. Rare earth diagrams. Conventionally, we report data for rare earths by plotting the normalized abundance. Normalized chondrites, that simply means the concentration divided by the chondritic concentration. In this case, I've chosen to take the average of ordinary chondrites concentrations and use that as a normalization. If we do that, we can get nice smooth patterns. And the reason we do that, because if we don't, we get a pattern like this. Okay, this is a pure, if we just take, this is just the concentration actually in the CI chondrites in parts per million. And there's an up-down feature here which reflects nuclear stability and the way in which the elements are created. We can get rid of that sawtooth pattern by normalizing. So here, Here's Orgay. This is the classic CI chondrite. Has a concentration a little bit lower than the average ordinary chondrites because it's rich in volatile material. Mid-ocean ridge basalts, again, show this light rare earth depletion. Continental crust shows light rare earth enrichment. Europium behaves a little differently because it can take on a different oxidation state. So this is, when we see something like this, it's not smooth, we call it an anomaly. That would be a negative europium anomaly. And here's the mineral melt partition coefficients for the rare earth elements. See, most minerals of interest exclude the light rare earths. The europium anomaly arises because plagioclase actually accepts europium when it's in the +2 state. So we take a peridotite mantle composed of olivine, orthopyroxene, clinopyroxene, and maybe spinel or garnet, and then melt it. We can produce rare earth patterns like this, starting with a flat pattern. If we take garnet peridotite and melt it 15%, our rare earth pattern would look like that. Same 15% melting for spinel peridotite would look like that. 2% melting, like that. So we produce light rare earth enriched patterns by partial melting. The smaller the extent of melting, the more enrichment we get. The other thing is that the heavy rare earths actually partition into garnet and can be retained in garnet. All right, so rare earths in the mantle and crust. This is our diagram again. Again, we assume that as refractory lithophile elements, the abundances are the same as in chondrites, because we do have this problem of neodymium-samarium ratio being not quite chondritic. But I also have to tell you that the difference we're talking about in this from chondritic is about 6%, so it's not really big. All right, so again, we end up with the crust, typically light rare earth enriched. The mid-ocean ridge basalt, which samples mantle, from which melt has been previously extracted, is light rare earth depleted. Okay, another concept that's don't have too much time to talk about it. Mobility. Really, this relates to the ability of an element to dissolve an aqueous fluid, and thus the possibility of being lost or gained from a rock during metamorphism or weathering. One thing this means is that these mobile elements, alkalis, alkaline earths, uranium, are suspect if the rock is not truly fresh. And so, I mean, this is one of the problems with peridotite exposures is they're almost invariably metamorphosed and screwed up by crystal fluids. So we can't trust elements like that in rocks like that. The other thing is that these elements also concentrate in fluids released by dehydrating subducted lithosphere, and consequently tend to be present in high concentration in island arc magmas and in the crust. Lead in particular appears to be enriched in the crust as a consequence of this fluid transport rather than strictly melting. And I'm going to illustrate this with what geochemists call a spider diagram or a extended rare earth diagram. What we've done is taken some of these other incompatible lithophile elements and stuck them in some cases, into the rare earth pattern and tacked on to the left side. And we've ordered the elements in order of their incompatibility, so the extent to which they would be excluded from a mantle melt. If we look at in particular, the total continental crust, we see generally this pattern of increasing concentration with increasing incompatibility. We also see a couple of screwy things. We see a depletion in tantalum and niobium, and we see an excess enrichment in lead. These are kind of hallmarks of continental crust. Now, we can compare that continental crust, which is again shown in red, with some other kinds of, in this case, other kinds of lavas. Here's average mid-ocean ridge basalt. Continental crust doesn't look like average mid-ocean ridge basalt. Here is an oceanic island basalt from the island of Tristan da Cunha in the South Atlantic. it does not share this depletion in tantalum and niobium with the continental crust. It does not share an enrichment in lead with the continental crust. But if we look at an average intraoceanic arc lava, you can see this distinct similarity, enrichment in lead, depletion in niobium tantalum, that suggests that island arc volcanism has been a dominant mechanism by which the crust has been created, not necessarily the exclusive mechanism, but a dominant one. So we've grown the crust through geologic time, in large part by subduction-related volcanism. This depletion, niobium and tantalum, reflects the fact that they're held back probably in rutile and similar phases in the slab. On the other hand, the enrichment in lead probably reflects the fact that it can be complexed by chloride and transported in hydrous fluids in that way. Also note that there is excess enrichment in some of these elements in island arcs in the crust. Cesium, rubidium, potassium, excess enrichment, which also reflects its mobility, that is, its aqueous solubility. Okay, so now I want to talk about mantle reservoirs. So we've differentiated the Earth. We've made a core. We've made a crust. Turns out the mantle is not homogeneous. And one piece of evidence we have of that is when we look at basalts, we have a great variety of basalts. And we'll go back to our rare earth patterns. There's two fundamental kinds of basalts that erupt from the convecting mantle. I'm not going to worry about things coming through the continental crust because they can be contaminated by it or contaminated by the mantle lithosphere below it, or perhaps produced simply by melting of that mantle lithosphere, which is a trivially small fraction of the mantle. So we want to talk about the big parts of the mantle. If you look at the mid-ocean ridge basalts, they typically show this light rare earth depletion. Okay, again, this is what we'd expect if we remelted mantle which had previously lost a melt, that melt having gone to create crust, either oceanic or continental. On the other hand, if we look at oceanic island basalts, they're typically light rare earth enriched to varying degrees. Hawaii, Reunion, Samoa, Tristan, St. Helena, another island in the South Atlantic, typically light rare earth enriched. Again, this is suggesting that we have distinct mantle reservoirs. Broadly, one reservoir that gives rise to mid-ocean ridge basalts, one that gives rise to oceanic island basalts. The thinking is, wherever plates passively spread apart, we get this mid-ocean ridge basalt that erupts. Even in the Cayman Trough, this little spreading center in this fracture zone separates North and South America, a little bit of basalt that spills out there is sort of typical mid-ocean ridge basalt. That observation suggests that the source of mid-ocean ridge basalt is the uppermost mantle. On the other hand, oceanic island basalts or oceanic islands are associated with swells and other things that make us think they're associated with plumes from the deep mantle. So we think these other reservoirs are located somewhere in the deep mantle and brought to the surface by plumes. Okay, now we're this is just more of the same. Now show it with extended rare earth diagrams. Generally, the oceanic island basalts enriched in these incompatible elements, mid-ocean ridge basalts depleted in incompatible elements. Yep.
Are the ocean island basalts, are they enriched or just less depleted than the Morbs? In other words, is there a theoretical?
Oh, that's a good question. That's a really good question because I've cut a corner here. So even if we took a chondritic pattern, either rare earth or this incompatible diagram, a mantle with a pattern like that and melted it, it would be enriched. So you could explain this, and particularly if the extent of melting were really small, you could get some significant enrichment. But certainly Kilauea is not a really small extent of melting, and it still is somewhat incompatible element enriched. I think mostly, and the isotope evidence also suggests, I think that mostly these things have been enriched. There's been some process which has put back the incompatible elements into them. And so, yep, a lot of questions.
I have a question. I'm not a geochemist or a volcanologist, but those are two different processes and types of eruption. How do we know, or what about these processes do we know that it has to be a different composition of material erupting rather than it being a result of the two different styles?
The style of eruption has stylistically, these eruptions aren't that different. And mid-ocean ridges, we don't see it because it's typically happening 2 or 3 kilometers downward. One difference is that I mean, these are not, the oceanic islands typically don't erupt explosively. I mean, it's the island arcs that go off. These are quiescent eruptions typically. One difference is these are probably all generated at greater depth because lithospheric thickness, and if you're melting the mantle, you're not, almost by definition, you're not melting lithosphere. If you get it hot enough to melt, it's not lithosphere anymore. So you're going to be melting underneath the lithosphere. There's basically no lithosphere at mid-ocean ridge. That's melting that continues at a very shallow depth. Here, melting is probably much deeper. That's a difference. Also, it means that the extent of melting is going to be smaller here, but it's not style of eruption. It really does require. What's that?
At mid-ocean ridges, you could have circulation and things sitting around and moving by dynamic processes, and that doesn't change any of this.
Okay. The other thing that happens. The other thing that happens to magma almost invariably once it gets stuck in the crust is that once it rises into the crust, density contrast is reduced, it tends to stagnate and form magma chambers and crystallize. And I've totally skipped process of fractional crystallization. This also changes composition. But again, that affects both of these. You can't say it happens in one versus it happens in both. It's extremely rare when we get a magma that actually erupts on the surface without having been modified by crystallization. So there are a whole bunch of complexities, but none of which can explain these differences. Okay? And furthermore, if I can get to it, I'm going to be tight. The isotopes aren't affected at all by this, and we see this difference, fundamental difference in isotopic composition.
These are examples of hotspots, right, on these last two slides. Is it generalized to all samples?
Yeah, I've just kind of chosen some, I think actually mostly these are things probably that I analyze why I chose them, but no, I mean just a variety of hotspots. There are differences. What's that?
I think also you chose them probably because they're the canonical end members for Ian 2 and
Not strictly, no. No, I'm not trying to. And basically, I don't have time to get into that. I mean, if you want the short story, I'm giving you the short story. They're different. We can also identify different families. I like to think of them as genera of oceanic island basalts based on their composition. These break down further into groups. I think is Barbara's questions about, but I don't have time to talk about that.
I'm a little confused by this diagram versus the one before. Here is for your heavy rare earths. It's a bulk silicate earth normalized pattern.
Oh, right.
It's also but Chondrite normalized.
Right, yes. Typically for these spider diagrams, we use bulk silicate earth to normalize, whereas for the rare earths, just by convention, we typically use chondrites. Let's see.
Here, for example, the lowermost is a...
Yeah, you see, Basically, the bulk silicate earth probably has rare earth concentrations about 2 to 3 times what chondrites are. The absolute value is different, partly because the earth is depleted in volatile elements, and also because of the extraction of the core. But yeah, let's not worry about the absolute things. The question is, okay, so here's the thing. There's chemical heterogeneity in the mantle. Where does it arise?
I guess it's more about detail. So I see that Samoa is different from everything else in terms of cesium, lead, and strontium in this particular figure. Do you have an answer for that?
Do I? Yes. Okay, very briefly, Samoa, we have dead killer evidence that it is recycled continental crust that has been subducted in the deep mantle and returned to the surface. The rest of the stuff is a little more difficult to figure out. But again, maybe I think maybe I ought to give another 15-minute talk later in the week on mantle reservoirs. I don't have time to get into it right now, but you're quite right. There are differences between these. We can see it even better in isotopes. Okay, so as I guess everybody knows, is once we get below 660 in the mantle, the structure of silicate minerals changes. And as a consequence of that change, trace element partitioning changes dramatically. Okay, and this is what I want to. This is the point I want to make here. Ooh, wait a minute. This was supposed to have. Yes, I want to do this first. So, if I take my batch melting model, I take a 10% gonoprototite melt, and I get that pattern. Pretty smooth. Of course, that's because we've ordered these things based on how they partition from basically things like gonoprototite. Well, I take 10% of magnesium perovskite melt, I get that blue pattern. If I take a 10% melt of a mixture of basically a 1 to 10 or approximately calcium perovskite to magnesium perovskite melt, I get this pattern. The point is, if we now go and look at just a couple of these patterns, mid-ocean ridge basalts, Hawaii, society, they don't look anything at all like the kinds of melts I produce in the deepermost mantle. They look much more like this gonoprototite belt. Again, there's these lead anomalies. We can probably explain that by transport of lead into the crust by fluids. Okay, not every maybe potassium's a little funny, but on the whole here, these patterns look a lot more like that pattern than that. There's basically no way that you could explain the pattern of incompatible elements that we see in basalts by melting in the deep mantle. The point is, and we're now almost done, the point is that mantle heterogeneity is a consequence of processes occurring in the upper mantle. Okay, and furthermore, we have stable isotope evidence that allows us to deduce involvement of material from the very near surface, because it's basically only place you can fractionate stable isotopes. And so although plumes rise from the deep mantle, rock in them acquired its chemical properties in the upper mantle. So somehow we're carrying material from the upper mantle into the deep mantle. This is old cartoon from paper by Al Hoffman and myself. Either through subduction, that was we originally had in mind, but I think other ways to do this are subduction, erosion, and lower crustal foundering. Anyway, lithospheric material, one way or the other, getting down in the deep mantle and returning to the surface in plumes.
Can you not do this at the last stage of the plume, like when the plume comes back up?
Can I what?
Can you not acquire these characteristics from
back up?
Yeah.
Well, we acquired these things through melting. So for example, the depletion in mid-ocean ridge basalts, I need to get that by extracting another melt. Okay, so people have Good. Okay. I know what the answer is. Why we? Yes, I mean, people have suggested that, we create these by making a melt and let it percolate into lithospheres, metasomatism. Thing is, the isotope ratios tell us that these heterogeneities are quite old. Okay, so billions of, we're talking about heterogeneity created on timescales of billions of years ago. So it's not something that happens as a mantle plume rises to the near surface. If so, we'd be talking about timescales on millions or tens of millions of years. We're talking about heterogeneity that's hundreds to billions of years old, but not as old as the Earth. We're not talking about, there's no evidence that anything we see was created in the very early Earth. You were going to object to what I just said. And the one exception to that is, of course, Sujoy's xenon, which may well be original heterogeneity. Okay, I'm glad you corrected me. That's right. And that's an extremely subtle signal, right? Extremely subtle. And that's the only thing that I've seen that makes me think that there is, actually. Okay, I just wanted to, finally, radiogenic isotopes. And I think this is actually about the second to last slide. There's a whole bunch of elements that decay radioactively on very long time scales. Potassium to calcium and argon, rubidium to strontium. Lutetium to hafnium, neodymium, samarium to neodymium, rhenium and platinum to osmium. And these allow us to answer these questions of time scales because this occurs at constant rates. The other advantage to these are that they, in fact, are not fractionated by this. They aren't changed by this partial melting process, aren't changed by fractional crystallization. So it really allows us to identify mantle reservoirs. So we take two of these isotope systems. The samarium neodymium one, we represent the isotopic composition with this epsilon neodymium. This is deviation from the chondritic value in parts of 10 to the fourth. And strontium. We see this. This is the isotopic array. These are oceanic island basalts and mid-ocean ridge basalts. Mid-ocean ridge basalts, the red. And we can identify a bunch of classes of enriched reservoirs. So to answer Alan's question, so pretty much anything that's in this quadrant must have experienced incompatible element enrichment. Everything net averaged over the history of the Earth, everything in this quadrant's experienced incompatible element depletion. There's a number of pathways of enrichment, and a number of different reservoirs have been created. Different reservoirs have been created in the mantle. But again, I'd argue that all of them are in, all of that's been created in the upper mantle. Last slide, Bill asked me to make up a reading list. That's it. That's almost everything I've said today comes out of my textbook. So, okay. I know I was rushing.
So on your last slide, what's the difference between prima and poso and C?
In my view, nothing. They're different. It's the story of the Indians and the elephants in a certain way. They're different names for the same thing, and there is a common component. Here's the point, right? So prima, I didn't get a chance to explain this. Prima was originally coined by Zindler and Hart as prevalent mantle. And the point is, a lot of these arrays point back into this region. And this was rediscovered by Hart and others, and then they called it FOSO. It was rediscovered by Hainan and Graham. They called it C. Farley called it FEM. But the idea is there's a common component that there seems to be mixing between this stuff and a whole bunch of more extreme stuff. I think they're different names for the same thing, although people strictly... One paper might define it isotopically as is exactly this, another one is exactly that. But I think it's this. I think they're all talking about the same thing. The other thing is that it's in this region where we find the basalts with the highest helium-3, helium-4. Didn't have a chance to talk about noble gases, but helium-3, the Earth makes helium-4 by radioactive decay, by alpha decay, and the Earth constantly loses helium out the top of the atmosphere. If you have a high helium-3, helium-4 ratio, it suggests a relatively primitive mantle. So I think when we're looking at in this grouping in here is something close to, but not exactly, as close as the modern Earth can get to a primitive mantle component.
While I still have the microphone, I have another question.
Yep.
What is this term pyrrolite that you often hear about?
Oh, pyrrolite. That's a specific peridotite composition. Ted Ringwood coined the term from pyroxene olivine rock. Basically it's a variety of bulk earth composition, which I think is probably not dramatically different from yours.
As you said, it was a word derived from pyroxene and olivine, and when he originally put forth the term, he understood the melting relationship, and it's actually, original term was 3 parts Hosbergite, 1 part basalt. You mix them together and you get to the original composition. So he recognized the residue-melt relationship and approximated a primitive composition, as he called it, pyrrolite.
I think that term's tending to fade a little bit. Yep.
The oxygen isotopic composition of the Earth, Mars, that's different from the carbonaceous chondrite. So do you think there's a spatial gradient of oxygen isotopic composition within the solar nebula?
Yes,
Okay.
probably. And in fact, that gradient, well, at least the explanation for the oxygen isotope differences, the theory itself involves a gradient. It involves, I don't want to take up too much time here, but it involves photodissociation of probably water, I guess, in carbon monoxide in the solar nebula, freeing oxygen to then react with silicates. That's really what we have, or other oxidized solids. Carbon monoxide just never condenses. And so the idea is that you need 2 distinct frequencies of radiation to dissociate carbon monoxide, and because most of the oxygen is oxygen-16, basically you use up all the radiation that dissociates oxygen-16, and as you go out in the solar system, you can only dissociate oxygen 18, I guess that's the, no, use 16 and 18 and 17. Anyway, the oxygen isotope is now, variation now understood to be a photochemical process. It would involve a gradient.